Na festa do fim de semana, só um rolê bom. Ela chega e desencana com passo bem sou, passo bem sou, passo bem sou. Na festa do fim de semana. Festa do fim de semana, só um rolê bom. Ela chega e desencana com passo bem sou, passo bem sou. Na festa do fim de semana, semana, pana, 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 pana. Na festa do fim de semana. Pana, 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 de semana. Pana, 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 de semana. Pana, 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 de semana.
Hello everyone and welcome to a new stream. Today this is the second part of learning OpenGL and how this API work. Everything we will learn GLSL, the shaded language, and we will do everything we need to create something interesting, like to learn everything about graphics API, right? And this is what we are gonna do now. So we are going to learn all of this stuff and maybe create something interesting from it. So the last time we were watching the channel, and we will keep going watching the playlist. We will keep following that playlist. What we did the last time was we just wait. Let me just close Discord. Okay. What we did, we basically linked some API. Good afternoon, Ghost. How are you doing? Today I decided to learn OpenGL stuff and learn graphics APIs and how these things work. If you're interested in this, I would recommend following the stream because I think it's interesting. I don't know if you already know this stuff, but I personally don't really. Like, I know some things about OpenGL, but I still have, like, I know like 2% of all of this stuff, and I wanted to learn everything about OpenGL. Cooking lunch. Oh, that's cool. What are you cooking? What are you cooking? I can only cook pasta. Like that's the only thing I can cook. Oh, that's interesting. That's cool. It's a very important having OpenGL because I think it teaches you a lot because there are many things here for what I can see. Noodles with eggs. Oh, that's interesting. Are you from Asia? Where are you from? Sounds delicious. So, what we did so far, like I started the first part yesterday, and we basically we included the library. Then we created this function, but the the this main function, and all the code, like almost all the code, is inside the GLFW view documentation. And GLFW is a library that comes with OpenGL that uh, apparently makes you easier, like makes it easier to handle Windows and event system, right? So if you want to create Windows or um, make or handle events, GLFW helps you with that. And also we included glue, and glue apparently is a binding function because for what I learned yesterday, let me just open this. For what I learned yesterday, uh, this is our graphics card, right? You have our graphics card. I don't know which one you have. Like, let's pretend this is an Nvidia. Like so. What's the icon? Like this is the Nvidia icon. Yeah, it looks so real. So in your car manufacturer already implemented some functions in your GPU. Like you have okay some OpenGL functions in your GPU, right? This all of this is inside your GPU. Is it like your car manufacturer, your graphics card manufacturer uh, developed this and included OpenGL in your card, right? Because OpenGL probably already exists in your PC, in your graphics card. And what we need to do is with C++, we have to bind each function. Like we have to point every single function, and this is a platform specific. It's something like this to control our graphics card, and to simplify that, we use glue, and I don't know what acronym is this, but this simplifies the job. It's an header file, and this contains all the bindings. Look at this. Look at that. There are over 23,000 of code, 23,000 lines of code. It's like Jesus. Because apparently there are thousands of functions, and you have to implement it for each platform. For like Windows has its own implementation, Mac or Linux has their own implementation. Like it's a mess, but luckily we have Glue that does this dirty job for us, right? So thanks to Glue, we already have this binding. So we have this here. So the C++ API. With GLFW, we created a window and then we initialize it, right? If it fails, it will return an error, like it will exit and return -1. Okay. Then we have a window. We created a window using GLFW. I think this is the site. That's probably the title, and those two are flags probably. Yeah, I pretty sure these are flags. I can make my own game engines with OpenGL, right? Yes, you can. You can create game engines with OpenGL. It's like OpenGL is a graphics API, is cross-platform. So if you are, you know, if you there are many ways to, like, there are many choices, and you can create like platform specific or platform dynamic or cross-platform game engines. OpenGL is cross-platform, so if you are like alone, or you're coding, you're a single person coding everything, I would recommend using OpenGL, because if you use other platform specific, you have to create their own implementation for that platform. Like if I remember correctly, Windows uses Direct 3D, DirectX for graphics, right? And OpenGL is kind of cross-platform. So if you are like, if you have a small code base, I recommend using it, and learning it is really worth it, in my opinion. And okay, if the Windows somehow fails to initialize it, we always terminate this and exit. Then we have to create a context. I don't know what a context is exactly. Like you make the Windows context current. I honestly don't know, but when you initialize Glue, and we initialize it here, you have to create the context first. That's what I learned yesterday. It's for what I see, like where is it? Hold on. Let me search the documentation. So we have Glue documentation. Probably usage. Yeah, it's written right here. First, you need to create a valid OpenGL rendering context and call Glue init. And that's what we did here. We created a context with glfw make context current, and then we called Glue init. Then we started following this part, like we created some vertices, like we created an array of vertices. This is what I'm trying to do. What I really recommend doing is watch. There is a YouTube channel called the Cherno, and if you watch the previous live stream, that's what we did. Like we basically are following this playlist, and this guy explains everything. So I really recommend watching this. if you like wanna to, if you like are very interested on, on this stuff. This is what I learned yesterday, and another important thing that I can resume is OpenGL is a state machine, like is a stateful, how can I say it, architecture, right? That means that OpenGL is like if you wanna render stuff, like you have, wait, what the, okay, if you are using OpenGL, you have like a selector, right? These are like some buffers, like you have a set of buffers right here, and then you have to select this. You have to bind each buffer to use the functions. Like you select this buffer. This is a bind using the bind function. So so what we did here, we generate a buffer, and then we bound it. We bound it. Oh god, my English is not that great. We bound this buffer here that we generated. So we generate buffer, and this buffer is like a block of memory that is stored inside of your VRAM. So this is your GPU contains the VRAM, and it's stored right here. So these blocks of memory are stored inside your VRAM. So this is basically how it works. And if you want to, handle data, like if you want to draw a triangle that it's stored here, like you have a triangle stored here, you have to bind this and then call the draw function for it. Like it, of course, there is a specific function for it, and I don't remember which one is it. After you bind the buffer, right? So this block of memory contains the information for the triangle, and then you call draw. This is pretty much how it works. It's a stateful architecture because you bind the states, right? And that's what we did here. We created this is a buffer. Like this is the unsigned int is, it stores the ID of the buffer. So we store buffer ID here because each buffer is assigned with an ID. Then we generate the buffer. We pass the memory address of this variable, so the function automatically assigns the buffer. Then we bind it, and then we allocate this memory. Like I think this allocate memory in the VRAM. I think this function is what it does. Like GL buffer data, it allocates memory for the VRAM, and there are, I think, let me just, and there are like some flags, like there are some methods that I honestly didn't understand how these flags work, but then you have to pass, the ID of the buffer you just generated. And this is pretty much how it works. And then you have to draw the arrays you just generated here. Like, we created this array, we binded it, and then we can call draw. Like, that's what we did here. Like, this is the bind part right here. Bind, and this is the draw part. Okay. I don't know. I try to be. I try to explain it. I'm not good at explaining things, but I hope you understand something on how this works. So what we are gonna do, we are going we are going to keep watching the. Wait, it's not here. Wait, am I still streaming? Okay. So we're gonna keep watching this this playlist, because this is. I think that Charno is really good at explaining this. So we just finished watching the 4th video. This is basically what we learned yesterday, right? And after I. No problem. Just keep trying, and you will improve. Thank you so much. Thank you. I really appreciate your support. So let's keep watching the 5th video. Holy shit! I fucking hate. I don't care. Go away.
Guys, my name is Chen and welcome back to my OpenGL series. So last time we talked about vertex buffers. There's a link up there if you haven't seen that video, but there were some parts that we were missing to actually get our triangle rendering. And specifically
Oh yeah, actually, okay, I forgot to mention this is the vertex buffer. Like, we have these are the vertex position. These are vertex positions, X and Y position to render a triangle. There are three vertices, and this is the X and Y position. This is pretty much how it works. And to make OpenGL to make OpenGL understand that these are the vertices, you have to specify this is a array buffer, because this is stored inside of an array, for what I understand. So let's keep watching this.
The major parts that we were missing were vertex attributes and shaders. Today we're going to cover vertex attributes. So what is a vertex attribute? So basically the way that the OpenGL pipeline works is we've kind of discussed lightly in the last episodes, and we will have some kind of in-depth video on that in the future. But to put it simply, the way that the OpenGL pipeline works is that we basically supply our graphics card with data, we store some kind of memory on the GPU, which contains all of the data of what we want to draw, and then we use a shader, which is a program that is executed on the GPU to actually kind of read that data and display it on the screen, more or less. And typically the way that we actually draw geometry is we use something called a vertex buffer. That is basically a buffer of memory that is stored on the GPU. So when the program, the shader, actually starts to read that vertex buffer, it needs to know the layout of that buffer. What is actually contained in the buffer? Is it just a bunch of floats which dictate the position of each vertex? Do you also have texture coordinates, normals, anything else like that? We have to actually tell OpenGL what is in the memory and how it's laid out, because if we don't do that, then as far as OpenGL can see, it's just a bunch of bytes. It's the same as with C++, right? I mean, if I write a float and I assign it something, we know that the memory there is a float because I'm telling C++ this is a float. If I cast that to an integer if I cast it to an int pointer, if If I take the memory address of the float and cast it to an in pointer and then dereference it, I'm going to get something completely different because it's interpreting the memory differently. That's kind of the same thing that's going on here. We need to be able to tell OpenGL the first 12 bytes are 3 floats, 4 bytes per float, and that is my position. The next 8 bytes after that are my texture coordinates. I've got 1 float for X and 1 float for Y, or U and V if you want to call it like that. We need a way to be able to tell OpenGL this is the layout of my memory, and that is exactly what this whole vertex attribute pointer thing can do for us. There's a function in OpenGL called GL vertex attribute pointer. That's what we're going to be taking a look at today. From the shader side, you also need to match the layout that you define on the CPU side, on the C++ side as well. And when we actually introduce shaders in the next episode, we'll take a look at a basic example of what that looks like as well. And again, I'm just starting off with really basic examples so that you can see what it is like in its simplest form. But as the series goes on, we are obviously going to ramp it up and make it way more complicated. I'm just kind of starting you guys off gently. Alright, without just rambling on further, let's take a look at the code. So from last episode, we have basically a float array of positions here. You can see that the way that I've kind of divided it is that each line here is an actual vertex, right? So we have 3 vertex positions, we have 3 vertices. This is the X coordinate, this is the Y coordinate of our vertex on our screen. Now before I go on, I just really want to define what I mean by vertex, because people seem to get pretty confused with that and also use that word incorrectly. A vertex has nothing to do with a position, right? A vertex is just a point that is on your geometry. The way that most people think about them visually, obviously, is by its position. So if I draw you a triangle, you'll be like, 3 vertices. But vertices are not positions, right? A vertex is not a position. A vertex can contain way more than just a position. So if you tell me, hey, I have a vertex, it's 0.5, 0.5, that doesn't tell me anything, right? Because you're kind of implying that I mean vertex position. And yes, a lot of people do use it like that, but that's not exactly correct, because a vertex can contain way more data than just a position, although it does usually contain a position. So I just want to make that clear. When I say vertex position, that's what I really mean. I'm not going to just, if I actually say the word vertex, I mean the whole blob of data that makes up that vertex, which again could include the position, texture coordinates, normals, colors, binormals, tangents, all of this kind of stuff, right? That could all be in a single vertex. So just the position, if you're just referring to the position, you should really call it positional.
Well, yeah, okay. A vertex is way more complicated than a toad. So, yeah.
Vertex position. So that's why I've got this float here as kind of positions, not just vertices, because at the moment they're just positions. Although when I add stuff to them, I really probably should rename them. Anyway, so we have these 3 vertices here, and then we're generating a buffer, binding it, and then actually putting this kind of, or I should say copying these positions into this actual buffer that we've defined here by just specifying a pointer to them and how big they are. And that's it. That's all we're doing so far. So again, OpenGL has no idea that if you look at this code, we can clearly see, okay, so we have 2 floats per vertex, and that is the X and Y position, right? OpenGL doesn't know that. It might seem obvious to you because you're looking at this code and you're like, well, how can OpenGL not know that? But what if I suddenly introduce a 3rd kind of coordinate, right? So in other words, what if I want a 3-dimensional coordinate system instead of 2-dimensional like we've kind of got here? What if I do this? Well, then suddenly, you know, how does OpenGL know that I've actually got 3 vertices of a 3 kind of dimensional coordinate system instead of just 1, 2, 3, and then kind of 4.5, I guess, of just 2 coordinates, right? Because if I was to rearrange this code, well then suddenly it looks like we actually have more than 3 vertices here, if you kind of stick to the kind of 2-dimensional rule, right? So what I'm kind of getting at is that we need to tell OpenGL our layout, and that's what we're about to do. So if we scroll down a little bit, once we kind of bind the buffer and we fill it with data, you don't have to do this before you fill it with data, you don't have to do it after, you can do it whenever, as long as the buffer is actually bound. That is when we can tell OpenGL what the layout of our buffer actually is. And the main way that we do that, if I just open up my favorite documentation website here, docs.gl, there are 2 kind of lines of code that we have to write. The most important one though is GL vertex attrib pointer, which is right over here, right? I'll click on the GL4 link, and we can see what we have here. So it takes quite a few parameters in. We've got the index, size, type, normalized, stride, and pointer. Let's go through them really quickly. So the index is the index of the generic vertex attribute to be modified. Again, this doesn't make much sense if you don't know how this works. Basically, the way that our shader reads all this is by an index system. Picture it as almost like an array, but the types in the array might be different. So this is an index as to which attribute you're actually referring to. All of these things, by the way, are called attributes. In other words, when I mentioned that a vertex is made up of more than just position, right? It might be position, texture coordinates, normals, colors, whatever. Each one of those, like a position is an attribute, a color is an attribute, a texture coordinate is an attribute, a normal is an attribute. They're all attributes. So this index is just telling us, hey, what index is this attribute at? The reason I say this is because typically if we have like a position, for example, at index 0, we need to be able to refer to it as index 0. So let's just picture this, right? I have three kind of attributes. I have position, texture coordinate, and normal. I need to be able to say that I want my position to be at index 0, my texture coordinate to be at index 1, and my normal to be at index 2. So that when I kind of start reading stuff from the shader side, from the GPU side, and I go into that buffer, I can simply reference them by, hey, index 2 please. And I know that that will be my normal because I've kind of defined that layout. So that's what an index is. It's just the index of that actual attribute in your buffer. Size here can be a bit missing.
So, okay, vertex attribute pointer. So you are like referencing the, for what I get it, you have like, for instance, you have an array right here, right? It's stored in your, this is stored in your VRAM, right? And then you have, okay, you have each individual elements right here, and you have like you might have more section, which this is the vertices. Then you have like, you know, UV mapping and things like that. Then you have to use what is the GL vertex attribute pointer. We will call it GL, just to simplify the job, and use and pass the index to, you know, to like map this attributes, right? This is what he's saying right now. Okay, so
misleading. It's the number of components per generic vertex attribute. You can see that it says here clearly that it must be 1, 2, 3, 4. So again, this size has nothing to do with bytes or like actual how much memory this occupies. It's basically the count. So what I mean by that is when we specify the type here, such as for our actual vertex positions, GL float, this is how many floats we're providing. So here clearly we have 2 floats per vertex.
oh yeah, that makes sense. Okay, so you also specify like how many, you know, how many dimensions you have per float. So you have two values for a vertex position. You specified right here, like you also specify like the dimension, right? Dimension, probably like 2D, 3D, 4D dimensions, right? Inside the count. Wait, is it the type or the count attribute? Let me just check this. It's the size. Okay, that's the size. Then we have, this is probably the type, right? No. The type is like, the type is the actual, wait, let me just point this. So we have the type, and this could be, you know, int, float, and things like that, you have you have these flags, right? And this is the index, of course. Like you have to specify the index. Like everything is mapped inside this function. Okay. So this is like the GL vertex attribute describes how to interpret this buffer, right? This is what I did understand for so far.
How many floats we're providing. So here clearly we have 2 floats per vertex. So this size will be 2 because we're basically providing a 2-component vector that represents our position. If we switch to that kind of 3D coordinate system, as I mentioned earlier, we would be setting it to 3 because we have 3 floats for this
exactly.
attribute. All right, so type, as I just explained, is basically the type of data that we're providing. GL float is what we want. Normalized, this is a little bit more tricky. We don't really need to worry about this, particularly if we're dealing with floats, because they already are normalized. But basically this is used for, let's just say that we're specifying a byte that is between 0 and 255, because that's our color value. That needs to be normalized to be between 0 and 1 as a float in our actual shader, and this is what will actually do it for us. So basically this is an example of something that you can do yourself on the CPU side, but you can also let OpenGL do it for you if you're lazy, or if you just want OpenGL to do it for you. So we'll be setting this to false, or specifically GL false, because normalized is actually a GL boolean, which is just an integer. All right, stride and pointer. This is where a lot of people get a little bit confused, so I want to just be clear on this. Stride is, as the documentation states, the byte offset between consecutive generic vertex attributes.
Good code is
oh my fucking god.
For everything else, there's centering.
This is worded in, I'm not sure why they
worded
it like this, but basically text attributes.
Wait, hold on.
GL false, because normalized is actually a GL boolean, which is just an integer. All right, stride and pointer. This is where a lot of people get a little bit confused, so I want to just be clear on this. Stride is, as the documentation states, the byte offset between consecutive generic vertex attributes. This is worded in, I'm not sure why they worded it like this, but basically what the stride is the amount of bytes between each vertex. So again, in our example, in our kind of made up example of we have a
so we have like 2 times the size of float, right? In this case,
we have a texture coordinate and we have a normal. Let's just say the position is a 3-component vector. The texture coordinate is a 2-component vector, or 2 floats, and then the normal is 3 components once again, right? So we have 3 floats, that's 12 bytes, plus 2 floats for the texture coordinate, that's another 8 bytes, so we're on 20 bytes, and then another 12 bytes for the normal, so 32 bytes. That is our stride, because it's basically the size of each vertex. The reason this is important is because if OpenGL, and the reason it's called stride as well, is because if we want to jump from one vertex to the next, so for example, I want to look up index number 1, so from 0, 0 is our first vertex, I want to jump to our second vertex, which is index number 1, I need to go plus 32 bytes into the buffer. So if we have a pointer to the beginning of our buffer, and I go 32 bytes into it, I should be at the very start of the next vertex. That is what the stride is, so just remember that. The point...
Okay, hold on, let me check if I see streaming. Yeah, okay. This is a little bit confusing, because like we have this, like this should be like the let me do this pink. So the size of in bytes of this section is the stride. This is what I understand. The other thing is like we have the vertices here, or maybe I think this is, hold on, wait, I got, wait, let me remove this because I don't think this is correct. So here we have the positions, right? And all of this is, this is a vertex. This is the information for each vertex for each vertex, right? And with stride we define the sides of each vertex, right? Then we have we give the index for each, you know, for each section. Then we have the sides for it and the type and so on. This is, there is, yeah, there is some information here to remember.
On the other hand, is thinking about buffer and I go 32 bytes into it, I should be at the very start of the next vertex. That is what the stride is, so just remember that. The pointer, on the other hand, is, as this states, an offset of the first component of the... I don't even want to read this, to be honest. It's so confusing. Pointer is a pointer into the actual attribute. So this is already inside the space of the vertex, right? So you're just pretend, don't worry about how many vertices you have anymore. Pretend you only have one vertex. I have one vertex, and inside there I have position, texture coordinate, and normal. What is the offset of each of those in bytes, right? So for position, the offset will be 0 because it's the very first byte of our buffer, the very first byte of our actual vertex is the position, right? Then we go 12 bytes forward, and we reach the beginning of the texture coordinate. So for my texture coordinate attribute, this value would be 12 because 12 bytes into it is where we begin. And finally, 8 bytes into that, we get to the vertex normal, right? So 20 bytes from the beginning is my vertex normal. So for my vertex normal attribute, 20 would be the value of this pointer. Now, instead of just writing generic things like 0, 12, and 20, because that can get a bit confusing, and not only that, but if you actually rearrange your layout or something like that, you'll have to recalculate it all manually. There are macros and kind of, well, it really is a macro called offset of. I actually demonstrated that in the arrow operator. If you guys watch my arrow operator video, which you should because it's important for C++, I actually kind of demonstrated offset of. I actually wrote it myself instead of using a macro, but the library actually, the C++ library and the C library provides you with an offset of macro, which you can use to actually find the offset of something in a struct or a class. So you can use things to kind of, same with stride as well, you can use kind of macros and stuff like that to automate this stuff for yourself so that you don't have to just be putting values like 12 or 32, as I said, for the stride manually. I'm just explaining to you what they actually should be, but just hopefully this explains the entire kind of vertex attribute pointer function to you, because again, it's something that can be confusing if you're just starting out, but it is actually really simple, and make sure that it's correct, because if you get even one byte kind of out of place here, you're going to get weird artifacts probably in your rendering, or just a black screen or something like that. Okay, so back.
Okay, so this is actually the, wait, what's the attribute? Hold on, let me read this. So this is the pointer, right? So we have a pointer, and then we have and each pointer is probably set with an index, right? So we have a pointer for this section, a pointer for this one, and another pointer for this section here. Yeah, probably this. So let's.
You're gonna get weird artifacts probably in your rendering, or just a black screen or something like that. Okay, so back here in our code, we can finally use this now. So what I can do is, with the buffer actually bound, that's important, I'm just going to write GL vertex attrib pointer. All right, so again, first parameter is the index. Now, this is a really simple case, as I mentioned earlier. We just have positions. So first of all, we only have one vertex attribute, so we only need to call this function once, because we're just specifying a single attribute here. The index, of course, will be 0, because it's the first attribute. The size, remember, the size is the component count, not anything to do with actual.
Wait, what is exactly the index? Hold on, let me just docs.gl. So we have attrib pointer. Wait, what's the name? I forgot. Vertex attrib pointer. We also have attrib pointer v, but I think that's what we are looking for, right? Yeah. So let's click on that. Specify the index of the generic vertex value to be modified. What? Wait, what? Oh, okay, I get it. So this is actually what this. So the index is actually the like, how can I say that it specify if you are modifying the text code, the normal, and the positions. Like this is the index, right? So the index is just, and let me get rid of this. So actually we have this part right here, like this label is actually specified on the index. So we have index right here, and probably 0 stands for position, so this will be 0, right? So you have to map your own memory, right? This is pretty much how it works, right?
Actual size in bytes. So how many floats represent this specific vertex attribute? 2. So I'm gonna write 2. Next we have, well, this one.
Hold on, let me try to do it by myself. I will fail definitely, but let's see. So we have the index, and the index is actually okay. Let's see. We have GL vertex attrib. Oh my, vertex attrib pointer, right? So we have this. So we have specified the index, which is like the type of value. Then we have, what do we have? The size, and then it's a 2D. So it's a 2D. So we have to put a 2. Then we have the type, and we have to specify GL float right here. Let's say. Then we have normalized, and yeah, he told us before to set it to false since floats are already normalized. Then we have the stride, and honestly the stride should be 2 times sides of weight. I actually don't know, like for now we have 2 times sides of float, right? But this isn't the case. Like this is just for the positions, for the position buffer. We also have to consider the other the other attributes, right? So we probably need to make a sum or something like this. So I will just leave it empty. And then we have the pointer, and the pointer I think is just positions, because that's pretty much yeah, that's the pointer of the array, right? I'm not sure. I probably did something wrong, but let's try to test this. So let's try to.
Anyway, next we have the type. So this is going to be the type of data that we have here. Clearly these are floats, so we're going to type in GL float. Next we have whether or not we want them to be normalized. No, they're already floats, they're already in the space that we want them to be, so GL false. Next we have the stride. Now as I mentioned, the stride is the amount of bytes that we have between each vertex. So this is our first vertex, second vertex.
Oh, so that's the size of each of each section. So this is actually this. Okay, so I did it right before, so I put this back here. So this should be, yeah, right? That's right.
Third vertex, clearly the stride is the size of 2 floats, right? So what we could write is just 8, basically. We could
it's basically
also write size of float times 2.
Yeah, that's what I did.
The best way to kind of automate that, so to speak, and make it as easy to read as possible here, because we're not dealing with something like a struct or anything like that. Eventually, when we have more than just kind of a position per vertex and we start to introduce things like texture coordinates and normals, we will have a struct that makes up a single vertex, and in that sense we could just pass in the size of that struct as a stride and that would be fine. But for now, size of float times 2 is how much you need to go forward to get to the second vertex. And just to make that super clear, because we only have one attribute here, it's the amount that we need to go forward to get to the second vertex, not the second attribute, okay? That's kind of what this next parameter is, the pointer. Now, keep in mind, you can see here that it's actually a pointer. It's taking in a pointer, not a number. So this might be a little bit confusing, but it is still just a number. Because remember, pointers are numbers. If you don't understand pointers fully, watch my video on pointers up there, because that's going to clear so much up for you. So since this particular attribute is the first, and in this case only attribute, this is just going to be 0, and you can just pass it in like that.
Oh, okay. It means the actual pointer for this instance. Okay.
If we had another attribute, for example, let's just say texture coordinate kind of started here or something like that, then we would actually have to pass in the offset to that texture coordinate, which would be 8 bytes. So we could just write 8 like that. If you try and do that, you're going to get an error here because we're trying to pass in 8 and it needs to be a const void pointer. The way you fix that is you just cast 8 to a const void pointer. Might seem a bit dodgy or whatever, but it's totally fine. That's what you're meant to do. And of course, if you were doing this properly and you had a real kind of application or engine or something like that, you would probably have a struct to actually define your vertex, and then you could just use the offset of macro to figure out what this is for you instead of just writing 8 or something like that, because that's not a good way to go. Anyway, of course, for us, it's 0. There you go. That's it. That's how you use this function in this case, and it should work just fine. But wait, there is always something that I forget that you need to write to actually make this work. I always forget this when I start writing OpenGL stuff from scratch, because obviously if you're kind of like me, you don't typically write code like this often, because this is something that you kind of do the first time when you're setting up a new engine and then you forget about it. But there is one more line of code that we need, otherwise we are just going to get a black screen. And that is, we need to actually enable that vertex attribute. So back in our documentation here, I really wish that this documentation actually said something about enabling, or having to call enable. In fact, I don't remember if it does. Yeah, it does. At the end it says, to enable or disable a generic vertex attribute array, call GL enable vertex attrib array. So if we go to this function, you'll see what this does is it enables or disables blah blah blah, but basically we take in, this is the function we're interested in, we basically just take in the index. The index of the generic vertex attribute to be enabled or disabled. So back in our code, I like to do this before I do the pointer. It doesn't really matter. OpenGL, of course, is a state machine. It's not like it's going to check to see if it's enabled and then not do this if it's not. It doesn't work like that. You can call it any way you like as long as your actual buffer is bound. So we're going to call GL enable vertex attrib array, and then the index we want to enable, which is 0. Okay? And that is it.
Okay, so we just have to enable this. So why do we have to manually enable this? That I don't understand. Like, wait, what do you mean? There are more attributes. Wait, what? JL enable vertex array attribute. Oh, attribute array. Bro, what the hell? This is so confusing. So attribute array. These two are different functions. Honestly, this is a macro, but I think it's binding to a function. Yeah, it is because we are inside the glue header file. This is so confusing. Like there are like these two. Hold on. These two are two different functions. Wow. Like, oh my god. Okay, let's keep going.
These two lines of code are all you need to do in this case to tell OpenGL what the layout of our actual buffer is. And theoretically, if we had a shader, which we're going to have in the next episode, we'd be able to finally see our triangle on the screen. Going up here, I'm just going to remove this little error here, this extra kind of float that I added just for demonstration, and that's it. So basically, to summarize, this is the code that we've written today. Hope you guys enjoyed this video. If you did, you can hit that like button. You can also go and join my Discord at discord.com.
So let's try to repeat what we did so far. Let's try to make a summarization. So we using this function, we enabled the vertex, probably the vertex buffer, right? I don't know. Let's try to read the documentation. So we have probably GL. What's the function? Enable vertex attribute array. So that's basically what we are doing. We enable the attribute. So this is specific for the attribute, and we have the index, right? The index probably is the same index we pass here, and it's like the type of the attribute. It's the type of the attribute that we are going to enable, right? This is pretty much confusing, actually. So we bound this buffer. Oh, wait, hold on. GL bind buffer array buffer, then element array buffer. So we have so many buffers here. Like this is wow. This is confusing. So what we have, like we enable this this attribute, like we enable this attribute, and then we basically assigned the attribute for, and we basically mapped the vertex, the position attributes. We specify that this is a 2D. This is a 2D like vertex. The type and we use the floating type. Then this is the normalized function, and we set it to false. This is the wall sides of the position, and because it takes two floats, so we write 2 times sides of float. And I kind of forgot what this 0 is. Probably, oh yeah, that's the pointer. So it's taking the very first value, so we set it to 0. Wow, this yeah, there is some things to digest here, like, so for what we did so far. Okay, let's try to recap everything. So we included Golio, which is the binding function library. Then we included glfw3, which is the library that provides functions to handle windows and events more easily. Then this is the main function, and we have a window pointer, and then we initialize glfw. If this errors, we exit the program. Then we assigned window to a new window using glfw create window. This is probably the size of the window. This is the title, and these are probably the flags. Then we check if the window is initialized correctly, or else we terminate glfw and exit the program, right? Then we need a context, and I still don't know what a context is, and I will search for it soon. So we create a context, and then we initialize glue init, and we checked if it is initialized successfully, or else we can also return -1, because this is an error that shouldn't be here. So we will terminate the program. Then what we are doing here, we get the string, like we get a string like GL version, so we print the stringified GL version to the console, right? Then we have an array. We define an array of positions, right? And this is position is just an attribute of a vertex. So we created a buffer to store this array, and then we have a glgem buffer. So this is what we created. I don't remember what this one is. Oh yeah, this is how many buffers you want to create. So you specify 1, and then you create 1 buffer and assign an ID. So this is the buffer ID, right? So we bound this buffer to this array buffer. So since OpenGL is a stateful uses a stateful architecture, we always have to bind the buffers. Then I think we allocated some memory here. I don't know. I'm not sure if this is the correct description of this function. I honestly not completely sure, but that's what I understand. Then we enabled the attribute, because we have to enable individual attribute for what I get, and 0 is the position index, right? Then we specified the we mapped the position attribute using this function. So the index is 0 because 0, for what I understand, it stands for position attributes, right? And then we have 2 because we have a two-dimensional value, and this is a float. This is set to false. But that's the fucking what was the that's the normalized attribute, and then this is the size in bytes for each vertex attribute. Like this is 2 times float because this is a 2D vertex, and we are using floats, so we have the size in bytes, and then this is 0 because it takes the very first pointer, like the very first index of this array. This is for what I get. Then this is a loop, a loop GL clear. It refreshes the screen and it will draw a triangle, but not always. I mean, in this case, probably not, because we still have to define the data, how we map this data. Then I'm not sure what is this. The same. Oh, this is poll events. Probably something to handle the events. So if this window still exists, like it's not closed, we will run this loop, and then if we close the window, we will terminate glfw and then return 0. Yeah, this is pretty much what it does. Like there is some information to remember here, but we are slowly trying to get into this mechanism, and this is interesting. This is really interesting. So this is basically how it works, right? And yeah, I still have to to process all of this. Like I just started to to learn to I just started this a few hours ago, so I think I learned many things. Like I kind of knew some things, but like 10% of it, because like I had some OpenGL, like I had some experience with OpenGL, because when I was like 3 years ago, I created a mini 3D application using OpenGL. I can show you if you want. I don't remember where I saved this file, but it was I don't think I can find it. Jesus. It's probably stored. Where is it? So it's probably stored right here. So we need. Let me just try to search this. Oh, this will take a while. Let's see. Am I still streaming though? Yeah, I'm still. Yeah, I'm just afraid to, I call it Megatron, and this doesn't have anything to do with transformers. I didn't know that there is an element in Transformers that it was called Megatron. This is not it. This isn't a Transformers reference. Like I didn't know what. Like I didn't know that until my friend, like some people told me that it is from Transformers. Like I didn't know that. I just called it Megatron because it is inspired from it is inspired from Tron, the game Tron, right? Uh, yeah, this is taking too much. But I tried, like it's not a functional game. Like it's just a model of it. Yeah, it doesn't even. It, I can't even find it. Like it's not there. Like oh my god, I hate finding like old stuff that I made 2 or 3 years ago. But this is like where I try to experience with OpenGL and stuff like that. Pretty interesting though. So I will take a short break. So I will see you very soon. Let me just where is this file? I will just put this here and mute myself. Okay. See you in a couple of minutes. Okay, we are back. We're back. Jesus, this is yeah. I needed a short break, because we have to memorize all of this. Like we don't have like to just memorize the function. We have to have a deep understanding. Like it's like a programming language. Like you memorize the functions, the methods, but you have a deep understanding of what's going on, right? Like you know how strings work and things like that, and the methods or function to handle them. The same things applies on OpenGL, right? So I don't know if every single um, like graphics API is like a stateful machine, and it has a stateful architecture, and you have to to bind all of this, and you have to map the data. Probably something similar, like or we have the same thing or something similar. Basically, this is basically how it works, right? Yeah, it's it's not immediate, but we have to slowly learn this stuff. Also, I want to announce that we opened our Discord server. Where is it? Let me check something real quick. We finally open it. So we have this server right here. Let me create a new invite. So we have a new invite link, and this is actually pretty much how it works. Like, let me just create. Wait. Edit invite link. We have never here, and then generate a new link, and we should have a new link, right? Wait, where is it? Where is the new link? Wait, what? Wait, it didn't. Oh my god! It. Oh, okay. Let me just. So we set this to never. So let's generate this and let's copy this. Right now we should have a new invite link. Let me try to I cannot change the settings. Damn it! I'm just gonna copy and paste the new invite link here. Let me try to. So we have this Discord. Wait, this is the wrong account. Hold on. Where is it? Where is the other browser tab here? So we have this. Now let's paste our Discord link. This Discord, and this is this is on the Discord link. What the fuck? Did you actually copy this? Oh my fucking god. Discord, are you fucking serious? What the hell is this? I wanted to create a new link. Yeah, generate it, copy it, but it copied this fucking thing. Like, look, if I go here and paste this, it just hit and use Yeah, I was muted the whole time. Or did I accidentally mute myself? I don't know. Let me just go to the... Okay, let me... Okay, I muted myself, but I... Oh my fucking god. I muted myself, but I didn't... I didn't censor the screen because I'm fucking stupid. Okay. Let me enable the streamer mod so I don't get. And now we are back. And the status will reappear magically. That's cool. That's cool. Okay. Did I? Yep. So let's keep going. Let's keep going. And let's do everything we can to, you know, do this. So we have the okay, everything works. Now let's keep should we keep watching this or should we read more documentation? What should we do right now? So we have GL enable vertex array. Let's try to read the description of it. GL enable vertex attrib array and JL enable vertex array tree attrib. What the hell? Va object. Oh, this is basically the same function, but I don't know. I don't know. Specify the name of the vertex array object for. Okay. And with ID va object. And we have errors. This is the return value. Is this the return value? I think so. After we bound the buffer, we have to generate to enable the attribute before we draw. Before we map the attribute, right? So we have to bind it, then we have to enable it, then we have to map it, and then we can draw it. Okay. We can also get vertex attribute with argument index and GL vertex attribute array enabled. Don't know what that is. Get vertex attribute pointer v. Let's try to check this one. What the fuck is this? GL get vertex attribute return a generic vertex attribute parameter. So we can actually get from them using GL get vertex attrib. Oh, this is kind of tricky. P name params. So we can return the type, the size, the reinteger, normalized, stride, enable, divisor, jQuery, and vertex attribute. What? So let me check my new Discord server. So this is I still have to set the welcome page, but anyways, let's watch the. So I think I'm starting to get how things work, right? So we still have to watch 26 videos, 25 videos, right? And then we can, so let's try to continue how shaders work in OpenGL. And a shader is a software, is a program executed on the, but it's a program, it's a fucking, god, why do I struggle talking? Okay, a shader is basically a software, a program executed by the GPU, right? Let's keep watching the video. Oh my fucking god, not this fucking ads again. I don't care. Go away.
Guys, my name is Eterno and welcome back to my OpenGL series. So today we're going to be talking all about shaders, finally, and we're finally going to be able to actually see something on the screen. So last time we talked about vertex attributes, and before that we talked about vertex objects and vertex buffers and all that stuff, so definitely check out those videos if you haven't by just clicking on the link up there. And from last episode, some of you were actually able to already see something on the screen, and if we dive into the code that we wrote last time over here, we basically just wrote these two lines. If I try and run this application as is without any kind of shader stuff at all, then you'll see on my computer it actually works. And we do seem to see a triangle, a white triangle, at our correct vertex positions, which we actually specified over here. So how come that's happening? And the answer to that is that some GPU drivers will actually provide you with a default shader if you haven't actually provided your own shader. And that's what seems to be happening here. But this is something that is really based on your drivers. Right now I'm just running this with the Intel drivers on this actual laptop. However, I do also have an NVIDIA GPU, which we'll probably have to switch to later for more serious things. But that being said, it's completely driver dependent, so I don't really want to that's why I didn't run it last time, and I don't really want to encourage that because it'll probably end up working for some of you but not for all of you, and then some of you will be like, my code doesn't work. It's not really meant to. There's nothing in the OpenGL standard that actually says you should see a triangle if you write the code that we've done right now. That's actually just up to the GPU manufacturers to say, hey, you know what, if you don't provide a shader, we'll just write a basic one for you so that you can at least debug your code a bit easier or something like that.
So it's kind of undefined behavior, right? This is pretty much what it is, right? So let's try to run this. And I tested this 1 year ago and I saw a triangle. Yeah, we can see it. We can clearly see it. So we have a triangle here, right? And we have the default shaders loaded by the GPU, right?
Today, we're actually going to write our own shaders. So the first question on everyone's mind is, what is a shader? A shader is basically just a program that runs on your GPU. That's all you should be thinking of when you think about a shader. By program, I just mean like a block of code. It's code that we can write as text, as a string on our actual computer. Then we can give it to OpenGL, we can send it to the graphics card, compile it like any other program, link it like any other program, and then run it like any other program. But the difference is that it actually is run on our GPU, on our graphics card, and not on our CPU like this C++ program is. So why do we need programs to actually run on the GPU at all? Why do we have to write code and then run it on the GPU? Well, obviously we're learning about graphics programming, so the graphics card does play a major role in that. But specifically, the reason that we want to be able to program the GPU is because, well, we want to be able to tell the GPU what to do. We want to utilize the power of the GPU to actually draw graphics on the screen. Now, that doesn't mean that everything we do, we need to do on the GPU, or we should be doing on the GPU in the form of a shader. There are some things that the CPU is still faster at, and as we kind of progress through this series, we'll probably find some things that we will prefer to do on the CPU, and then maybe just send the resulting data to the GPU while still doing that processing on the CPU. But that being said, there are undeniably a lot of things to do with graphics that the GPU is simply going to be way faster at. And that's where shaders come in handy. Now, not just when we want to defer things, not just when we want to kind of take things from the CPU and put them on the GPU, but fundamentally, we need to be able to program the GPU, because even in the form of drawing this really simple triangle, I still want to be able to tell the GPU how to draw that triangle, right? Like, where do the vertex positions go? What color should the triangle be? How should it be drawn? All that kind of stuff, right? When we actually get into more complex 3D scenes as well, lighting is a great example of why we want to be able to program the GPU. How does lighting work? All of that stuff, I don't want to get too ahead of myself, but all of that stuff needs to be programmed somehow. The GPU doesn't just know how to do this, right? We need to tell the GPU what to do with the data that we've sent it, and that is what a shader fundamentally is. Now, in this episode, and for most of OpenGL and for most of graphics programming, and you as well, are probably going to be focused on two types of shaders: vertex shaders and fragment shaders. Fragment shaders are also known as pixel shaders, by the way. So these two shader types are by far the two kind of most popular ones, and probably the ones that you will be using 90% of the time. There are other shader types: tessellation shaders, geometry shaders, that kind of stuff, compute shaders if you're doing like completely kind of other stuff as well. There are many different types of shaders. Don't think that there are just vertex and fragment shaders. That's it, you're done, that's all there is. There's much more. And they do come in handy when you kind of start getting to the more advanced stuff. And we will certainly be covering those types of shaders further down in this series when we get to more complex graphics. But for now, and for like 90% of shader programming, you're probably going to be dealing with vertex and fragment or pixel shaders, right? That's it. So first of all, let's talk about what that actually means. What is a vertex shader? What is a fragment shader? What are they? Why are there two types? How do we use them? So I know I haven't really covered the OpenGL pipeline or just the standard kind of graphics rendering pipeline yet, but how this roughly works, or really the picture that you should be having in your head, is that we've written a bunch of data on the CPU, we've sent some data to the GPU, we've issued something called a draw call, we've bound certain states as well before issuing that draw call, and finally, we kind of get to the shader stage of things, or rather, the GPU gets to actually processing the draw call and drawing something on the screen, and we get to see a triangle on the screen. That specific process is basically the rendering pipeline, right? How do we go from having data to actually having a result on our screen? Now, shaders come in handy when the GPU actually starts drawing its triangle. And vertex and fragment shaders are two different shader types that are along that pipeline. So when we actually issue a draw call, what happens is the vertex shader will get called, and then the fragment shader will get called, and then we'll see a result on the screen.
Wait.
Two types of shaders: vertex shaders and fragment shaders. Fragment shaders are also known as pixel shaders, by the way. So these two shader types are by far the two kind of most popular ones, and probably the ones that you will be using 90% of the time. There are other shader types: tessellation shaders, geometry shaders, that kind of stuff, compute shaders if you're doing like completely kind of other stuff as well. there are many different types of shaders. Don't think that there are just vertex and fragment shaders. That's it. You're done. That's all there is. There's much more. And they do come in handy when you kind of start getting to the more advanced stuff. And we will certainly be covering those types of shaders further down in this series when we get to more complex graphics. But for now, and for like 90% of shader programming, you're probably going to be dealing with vertex and fragment or pixel shaders, right? That's it. So first of all, let's talk about what that actually means. What is a vertex shader? What is a fragment shader? What are they? Why are there two types? How do we use them? So I know I haven't really covered the OpenGL pipeline or just the standard kind of graphics rendering pipeline yet, but how this roughly works, or really the picture that you should be having in your head, is that we've written a bunch of data on the CPU, we've sent some data to the GPU, we've issued something called a draw call, we've bound certain states as well before issuing that draw call, and finally, we kind of get to the shader stage of things, or rather, we've issued something called a draw call, we've bound certain states as well before issuing that draw call, and finally, we kind of get to the shader stage of things, or rather, the GPU gets to actually processing the draw call and drawing something on the screen, and we get to see a triangle on the screen. That specific process is basically the rendering pipeline, right? How do we go from having data to actually having a result on our screen? Now, shaders come in handy when the GPU actually starts drawing its triangle. And vertex and fragment shaders are two different shader types that are along that pipeline. So when we actually issue a draw call, what happens is the vertex shader will get called, and then the fragment shader will get called, and then we'll see a result on the screen. Now, there are many things in between that I have skipped over for simplicity's sake. There are many stages.
Wait, let me just...
Triangle. And vertex and fragment shaders are two different shader types that are along that pipeline. So when we actually issue a draw call, what happens is the vertex shader will get called, and then the fragment shader will get called, and then we'll see a result on the screen. Now, there are many things in between that I have skipped over for simplicity's sake. There are many stages before the vertex shader, many stages in between the vertex and fragment shader, as well as between the fragment shader and the rasterization stage and all of that stuff. I don't want to really cover that right now. I'm trying to keep this simple, so just keep that in mind, all of you advanced people who know exactly what's going on but are still watching these videos for some reason. I'm kidding, by the way. Pretty much everyone should watch these videos because it might fill in a lot of gaps that you're missing. But anyway, the point being, I am simplifying this. So we go from the draw call to the vertex shader to the fragment shader to being able to see pixels on our screen. Now, what the vertex shader does, or specifically the code that is our vertex shader, that gets called for each vertex that we're trying to render. So in this case, we have a triangle. We have 3 vertices, okay?
Yeah.
That means that the vertex shader will get called 3 times, okay? 1 for each vertex. And the primary purpose of a vertex shader is to tell OpenGL where you want that vertex to be in your screen space, right? So again, simplifying this, where in your window, you have a window open on your computer where you're rendering these graphics, where would you like that vertex to be, right? That is what the primary purpose of a vertex shader is. Just, again, it has the word shader in it, so some people like to think of it as having something to do with lighting or shadows, or no, it's a program. That's all it is. So this doesn't even have anything to do with actual graphics, traditional graphics in terms of like color or whatever. All the vertex shader does is it specifies where you want the positions to be. Now, that being said, it's also used to pass data kind of from attributes into the next stage. And then also, well, in our case, the next stage is the fragment shader. So it's also used for that because, of course, the vertex shader will actually take in all of the vertex attributes that we've specified in our buffer. In this case, we only have a position. These positions that we've specified, if we look back to our code, these kind of -0.5 and all of this stuff, we can access this in our actual vertex shader, because we've actually specified them as vertex attribute pointers, and you would have noted that we also wrote the index 0. And this index 0 is actually...
Hey everybody, it's Tony Robbins and Dean Graziosi. I have a question for you. If you had to make a choice between...
No.
Actually going to correspond to an index 0, which we'll define in our actual vertex shader, that we also wrote the index 0. And this index 0 is actually going to correspond to an index 0, which we'll define...
Wait.
Actually, we can access this in our actual vertex shader, because we've actually specified them as vertex attribute pointers, and you would have noted that we also wrote the index 0. And this index 0 is actually going to correspond to an index 0 which we'll define in our actual vertex shader, and through that kind of format we'll be able to actually access the data, or access this specific vertex attribute data, this specific vertex attribute being the position. So once we've accessed that position in our vertex shader, we can basically tell OpenGL, I want you to position this vertex at the position that we specified in the attribute. Now, you might be thinking this is a very, very trivial task. Like, why does this even need to exist? Obviously, we want to position our triangle or our vertex position where we've actually specified in our buffer. Well, yes, but think about this. What if you have a camera? You have a camera in a 3D world, and its position is somewhere. Suddenly, these vertex positions that we've specified for our triangle aren't really going to translate directly to being on the screen at those same positions, because if the camera's moved, then, well, the triangle should move as well, and that kind of transformation of that triangle needs to happen somewhere. Now, this comes down to certain things being faster to do on the CPU and the GPU, and there's a lot of thought that goes into this, and we'll certainly cover it when we get up to writing cameras and stuff like that. But all I'm saying is that don't think of it, it's not actually that trivial as just saying that the data that is in my buffer, that is where I want my vertices to be, because there are certain transformations that actually need to happen based on certain states and just a lot of other stuff as well. But again, the primary purpose of a vertex shader is to provide those vertex positions. We need to be able to provide some kind of transformation if necessary, so that OpenGL can actually transform these numbers into actual on-screen coordinates, so that we see our graphics in our window at the right location, in the right place. So once the vertex shader has run, now remember it runs for each vertex, once that's happened, and we've run it in our case 3 times, it gets called 3 times, 1 for each vertex, we move on to the next stage in our pipeline for this application, which is the fragment shader or the pixel shader. Now, fragments and pixels are a little bit different kind of terminology. We're not going to get into that now, but for now you can kind of think of pixels as or rather you can think of fragments as pixels, because the fragment shader is going to run once for each pixel that needs to get rasterized. What I mean by rasterized is actually drawn on our screen. So our window is just basically made up of pixels, right? It's like a pixel array. What needs to happen is those 3 vertices that we've kind of specified that make up our triangle now need to get filled in with actual pixels. That's what the rasterization stage is doing. And the fragment shader or the pixel shader is going to get called once for each pixel in our triangle that needs to get filled in. And the primary purpose of our fragment shader or our pixel shader is to actually decide which color that pixel is supposed to be. That's all it does. It determines a color, an output color for our pixel, so that we can get so that the pixel can get shaded with the right color. Think of this as like a coloring book, where you've kind of got an outline of things, but you need to actually color it in. You need to shade it in with a certain color. That's what the fragment shader is responsible for. Now, straight away, you might have noticed a difference between the two. Vertex shader gets called 3 times. Fragment shader might get called
1 million.
Tens of thousands of times, right? Yeah. Depending on how much room our actual triangle occupies on our screen. If you have a tiny triangle, a really small triangle in your window, that might only get called like, I don't know, 50 times or something, maybe, if it ends up taking up 50 pixels. If you have a giant triangle just filling your window in OpenGL or something like that, it might be taking up like, I don't know, 1 million pixels or 500,000 pixels or something like that, which means that fragment shader is actually going to get called 500,000 times immediately. And I want you guys to realize this even from the very beginning, that if I do something like 5 times 5 equal, like I calculate what 5 times 5 is in the vertex shader, and the value of that is 25, that calculation is going to happen 3 times in the process of rendering this triangle, because the vertex shader gets called 3 times. If we have a huge triangle and we do 5 times 5, that calculation in the fragment shader, and that fragment shader gets called 500,000 times, suddenly we're doing 500,000 multiplications and not 3. There's a bit of a difference here, right? Which is why when it comes time to kind of optimize and think about performance, which is really all the time, you can probably start to notice that, hey, it might be worth me doing some of these critical operations in the vertex shader rather than the fragment shader. And again, you can pass data from the vertex shader to the fragment shader as well. So yeah, just something to think about. Just wanted to mention that. Keep that in mind. Fragment shader, things in there tend to be a lot more expensive because that fragment shader is going to run for each pixel. That being said, some things obviously need to get calculated per pixel. So a great example, I love bringing up this example with fragment shader specifically, is lighting, right? If you're calculating lighting, each pixel is going to have a color value that is determined by a number of things. For example, the lighting, the environment potentially, the texture, the material that's applied to the surface, all of this stuff, right, comes together to determine what the correct color is for a specific pixel. Obviously, this is going to depend on a number of inputs, such as where the camera position is, and as I said, all the surface properties, the environment properties, all of that stuff is going to come together. But in the end of the day, at the end of the day, all you're determining in the fragment shader is the color of a single pixel. That is what the fragment shader does. It's a program that runs to determine which color this pixel should be. That's it. Once that happens, once that fragment shader gets calculated, your color will basically make it to the screen, okay? To your actual window that is open on your computer, and we'll see an actual triangle, a white triangle in this case, because the default shader in this in our driver seems to be just defaulting to white, which is probably a reasonable default. But anyway, when we start writing these shaders, it will be whatever color we specify. So as an easy test, we could just say that, hey, every single pixel for this triangle should be red, and we should just see a completely red triangle, okay? Fragment shaders run for each pixel and they determine the color output. Vertex shaders run for each vertex and they determine the position on our screen. That is basically how shaders work. Now, you may think that I'm really oversimplifying things because I am omitting a lot of the stages of the actual pipeline and a lot of other shaders that we actually have available to us, but I don't think I'm actually oversimplifying at all. That is actually as simple as it is. That being said, you can do some really cool stuff with this, right? You have something that runs for each vertex and for each pixel. With that, you can do like 90% of graphics programming. Everything you see in games nowadays is probably done 80 to 90% in those shaders, okay? And believe me, once you get to some really nice looking graphics, those shaders could be thousands of lines of code. So they definitely get very complicated. Not to mention that a lot of the game engines, and certainly every kind of serious big game engine, actually generates shaders on the fly based on what's going on in your game and based on what graphics settings you've selected and all that stuff. So having like kind of live shader generation and compilation is very, very common in game engines. So there's definitely a lot of really cool things you can actually end up doing with shaders. Anyway, that's a gentle introduction to shaders. We didn't get to writing any code this time, but we definitely will next time. I just wanted to give you guys a basic overview, finally kind of a bit of a technical overview of what shaders are, how they work, what they're used for and all that, and hopefully we'll see them in practice in the next episode. One more thing I want to mention is that like everything else in OpenGL, shaders work based on the state machine, which means that when you want to enable a shader, you're about to draw a triangle and you want it to use a certain shader to draw that triangle, you enable that shader. You might also send some data to the shader, so much like we're sending this vertex data from the CPU to the GPU in the form of a vertex buffer, we can also send data to our shader in the form of something called a uniform, and that comes from the CPU as well. So we kind of set up all of that state, enable the shader, and then we draw our triangle. That's how it works in OpenGL. Again, like the rest of OpenGL, it's pretty much just a state machine. If you guys enjoyed this video, you can hit that like button. You can also help support this series by going over to patreon.com/thechono. It really does help me make more of these episodes and more quickly and all that fun stuff. You also get some pretty cool rewards, such as access to all of the source.
Okay, that's cool. So what we learned is, actually, I already knew that, but let's recap this. Like we have so many types of shaders, right? And there are a big portion, and this big portion contains like, this is like the shaders, right? So we have shaders. This is a set of shaders, and there is a subset which contains two elements, which are the vertex and fragment, right? So this is pretty much how it works. So, and then there is other stuff right here, but these are the two main shaders that we are going to develop, right? To draw shapes. And of course the shaders is program run on the GPU, and I'm not sure if these are actually stored on the VRAM. Probably is, but that's good. Okay. Now let's keep going into this part. So let's okay.
My OpenGL series. So last time we talked all about shaders and we basically just went through what shaders are and how they work. Definitely check out that video if you haven't already. There's a link up there. You're going to need to know how shaders work because today we're going to write some shaders. And I'm actually really happy that we dedicated last video to just talking about what shaders actually are so that I don't have to do much talking today and I can actually write some code. So we're gonna just jump in and we're gonna start writing some code. If you don't have all of the code that we've written up to this point yet, you can either go through all of the videos in the playlist and just make sure you've got everything up to date, or you can actually go to patreon.com/thecherno, help support the series and get access to all of the code episode by episode up to this point and going on into the future as well. Let's dive in and write some shader code. So just to quickly go through all the code that we've kind of got so far, or at least the important parts, after we kind of initialize OpenGL and all of that, we're basically creating a vertex buffer which is consistent of these vertex positions. Positions are the only attributes that we're currently specifying. We then specify the layout of that buffer as well as kind of bind these attributes to a certain index number 0 in this case, via a vertex attribute pointer.
Yeah, but we still need to specify the other indexes, right?
And then inside our render loop, we basically just clear the screen, draw the currently bound buffer, which is this one over here, and then we just swap the buffers and that's it. We don't bother unbinding anything or anything like that. We don't really need to. All we're doing is we're clearing and we're drawing this triangle. Now let's go ahead and actually write a shader. So the first thing we actually need to do, and this is a little bit tedious, which is why I kind of want to run through this as quickly as possible, but basically we're going to define a new function here, which is basically, it's going to be static because I don't want it to leak into other translation units or C++ files. It's going to return an integer and it's going to be called create shader. And we're actually going to take in two strings, const std string vertex shader and const std string fragment shader. And inside here, we're going to write the code necessary to compile these two shaders. Now in this case, all we're doing is we're taking in the actual source code of the shaders as these actual strings. So we're providing two shaders, a vertex shader and a fragment shader.
Wait, are these shaders created in a single one shader? Like, we are returning a single integer, right? A single integer. And a single integer, I think this would be the ID of the shader, right? I'm not sure, but I see for what I see OpenGL typically works with IDs, right? You have IDs and you have bindings and things like that. I don't know. Let's try to create this function. So let's go here. And let's create a static. God fucking damn it! Static int create shader. Oh my god! Then we pass a const. Wait, is it const? Yeah, a const std. What the fuck am I writing? String, and then we have the vertex shader, then const std string. The other one was fragment shader, and then we have it. I will include an std string just in case. Like, I know it's already inside the IO stream, but I like to include individual elements that I use because the string actually doesn't include everything. Like, if you want to print a std string, you have to include this header. Like, it want to, like, if you want to std code vertex shader, it will throw an error. It doesn't. What the hell? Wait, I'm missing something. Wait, it doesn't actually throw an error. So wait, what the? Wait, I think it didn't compile this. Yeah, it didn't compile this. This is probably because it's static and we didn't call it anywhere. But if we try to call this create shader and then we pass two empty strings, yeah, we get a compilation error. That's because this should be return a value. Okay, let's try again. It works. I don't know, it works. Okay, but I will include it anyway because if I remember correctly, like for the cout you had to include the string, but for some reason it's not anymore. They changed something, probably the new standard. I don't know. But but I swear to God that you had to include this if you wanted to print an std string. But now it's not like this anymore. Okay, let me just get rid of this. Where did I write this? Right here. Okay, let's keep going.
Shader, these strings are just meant to be the actual source code. Now shaders can come from a variety of different places. We could literally just write a string in our actual C++ application which contains our shader, which is what we're going to do today just for simplicity's sake. But you can also read them in from a file, you can download them from the internet, you can read them in as kind of binary data. There's a lot of different ways that you can actually kind of compile shaders and get to the shader compilation stage. In this case, we're going to provide OpenGL with a string. At the end of the day, you still need to provide OpenGL with a string, which is your shader source code. Usually, like, you might want to be taking that in from a file or something like that. But for now, we're just going to be reading them in as strings, and we're going to write them in our C++ application. I think next episode we're actually going to take a look at how I like to deal with shaders in a more professional application, and we'll kind of write some code to basically simplify the further shaders that we're going to write in this series. But for now, we're just focusing on how to actually create shaders. So basically, the purpose of this function is to do, well, a couple of things, but fundamentally, we need to provide OpenGL with our actual shader source code, our shader text, and we want OpenGL to compile that program, link these two together into a single shader program, and then give us some kind of unique identifier for that shader back, so that we can...
Yeah, okay, I was right, so you have an identifier. But the thing I don't understand, like if we compile a shader, like is it supposed to return two IDs? That's the question I have. Let's try to
OpenGL to compile that program, link these two together into a single shader program.
Oh, okay. I didn't follow that part. Like I got distracted for a bit, but okay, I lost some critical information that this two gets compiled in a single shader, and the shader ID gets returned. Okay, this is pretty much how it works, right? Let me just check if it's still streaming. Okay.
Program, and then give us some kind of unique identifier for that shader back, so that we can actually bind that shader and use it, same as like we did with our vertex buffer, where we actually generate a buffer and we get an ID back, and then whenever we want to bind it, we can just bind that buffer ID. So if we scroll back over here, let's start writing that code. So the first thing we need to do is create a shader program. Now here we kind of generated buffers. That's basically the equivalent here. We basically just type in gl create program. Now again, this is lovely OpenGL being completely inconsistent. This function doesn't take in the reference to an integer or anything like that, or a pointer to an integer. It actually returns an unsigned integer. So what we're going to do is at the beginning just write unsigned int program, equals GL create program. Again, no clue why they've decided to be so inconsistent with their API, but hey, this is OpenGL. So the next thing we need to do is
Wait,
create
there.
our two-shader object. This function doesn't take in, because that's basically the equivalent here. We basically just type in GL create program. Now, again, this is lovely OpenGL being completely inconsistent. This function doesn't take in the reference to an integer or anything like that, or a pointer to an integer. It actually returns an unsigned integer. So what we're going to do is at the beginning just write unsigned int program equals GL create program. Again, no clue why they've decided to be so inconsistent with their API, but hey, this is OpenGL. So the next thing we need to do is create our two shader objects. So vertex shader and fragment shader. And this is basically just kind of some OpenGL boilerplate code. Again, unsigned int. We'll call this one VS, which is going to just be equal to GL create shader. And this is going to be the type of the shader, which in this case is going to be GL vertex
Oh my
shader.
god.
Now a lot of this code is actually going to be the same because basically we're just trying to compile two different types.
Okay, so we have the program. So now we have to create the shader. So shader, then GL, probably shader, probably vertex shader. Yep. And the other type is frag. Wait. This is the same thing. We have to create the fragment shader. So GL create. No, I mean GL fragment shader, like that, right? And we will probably call this FS, like form session, right? Let's see.
Types of shaders, but the process of giving OpenGL our source code and all that stuff is actually very, very similar between vertex and fragment shaders. So I'm actually going to just abstract this out into its own function so that I can call that function 2 times and not have a bunch of code duplication. So I'm going to go up here and I'm going to go static unsigned int compile shader, and it's going to be const std string source, and I believe GL vertex shader is actually, it's just an integer. I don't think they really need to. Let's just see what create shader takes in. GL enum, and I think if I search for GL enum here, just using Visual Assist,
Unsigned
it's an unsigned int. So I'm just going to write unsigned int type. Now I don't really like using OpenGL's built-in kind of types for several reasons, but mainly just because I tend to use multiple graphics APIs, and if I start using OpenGL's types for everything, then I kind of need to include OpenGL everywhere and all that stuff. So if you're seeing me kind of use unsigned int in these cases instead of kind of GLU int, oops, it's written like this, I think. Yeah, I don't like using types like this. I much prefer just using the raw C++ types, which they are anyway. That's just because I tend to deal with multiple APIs and that's what I'm used to. Just keep that in mind, you might have seen that before. It's definitely what I would recommend doing.
Okay, so let's create a new function, I guess. So we have static and compile shader. Oh my god. Then we have a constant std string. What the fuck? Then we have the source, and then we have an unsigned int, and I don't get what's the argument type. I mean the argument name.
GLU int. I have need choices instead of GL, and it's for here, just use type. Now I don't really.
Oh, that's the type. Okay. We call it like this.
Really like using open. Written like this, I think I've seen that before. It's definitely what I would recommend doing. Okay, so if we scroll back up here, compile shader, let's just move this code that we've got over here. Actually, I might just move this create shader over here and then just make, let's see, unsigned int id equals GL create shader. Okay, cool. And then we can kind of assign this to be compile shader.
Also, should be this be unsigned int? This is unsigned int actually. But I'm not sure if this should be also unsigned int because the program is an ID and the ID is unsigned int, right? Let's abstract this, of course. So we have probably we have the ID and then here's the type, right? then we have to use some bindings to specify the exact thing, like I don't know. So we probably use something like this to compile our shaders, right? And we have the source code here. Probably it works like this, but let's
This will be the vertex shader, and I'll specify that it is our GL vertex shader.
Yep. That's what I thought. And yeah, we already have the string for our source code, so let's put it's the argument. This is the GL vertex shader. I want to create a game. Like, I want to create a cool game, guys. You have no idea how cool the concept of my game is. So we are going to focus on that, and then we are going to create some games.
I actually think I'm going to reorder these arguments because it probably makes more sense to actually specify the type first and then the actual source code.
Okay, let's do that. Okay, so let's do this. Oh my god. Okay, let me just. I'm trying to follow the video because I know this person has a lot of experience for what I heard. So let's reverse the order, and then we have it right here. So we compile individual shaders, right?
So let's just reorder these real quick, no big deal. There we go. Alright, cool. So let's continue on with our compile shader function. One thing that OpenGL is actually going to want to expect is instead of us actually providing a C++ standard string, it's actually going to want a raw string. So I'm just going to write const char src for source, and then just set this equal to source.cstring, which we can write like this.
Can't just be passed the C3, or should we manipulate this in some way? No, I'm gonna follow his advice. So, done, and we have it right here.
This just returns a pointer, as you can see, it actually says in a comment, return pointer to null terminated immutable array. So immutable definitely means that you shouldn't be changing this, but also this is just a pointer to the beginning of our data. We could have also written code like this. You might have seen this kind of code.
That's weird.
Basically, this is just looking up the very first character in the string and then returning the memory address of it, which ends up returning this. Because the string API does provide us with C-string, I prefer to write this code. One thing I want to point out, this is more of a C++ thing, but just in case you do something crazy, source needs to exist at this point, right? This string needs to exist. This doesn't copy the array or return to you a new kind of array. This returns a pointer to the data inside std string, meaning that if string has gone out of scope or something and you're still holding on to this actual char pointer, it's going to point to rubbish memory, and this code isn't going to work. So just make sure that your source string is actually still alive at the time of you kind of compiling this code. Yep. Sometimes I see people kind of, get string.cstring or something like that. This kind of code is very dodgy. I might actually make a C++ episode on this specific kind of practice because it seems to kind of throw off a lot of people, and I can see why it's easy to miss if you're new to C++. But basically,
did you know the average person spends 3.5 hours?
Just returns kind of a temporary string, and you get the C string from it. Then that string might have gotten cleaned up, might have gone out of scope by the time we reach this line, which means that this kind of pointer is pointing to memory that's been freed already, and you'll get errors and stuff like that. Which is why my recommendation is also to kind of, if you've got a function which returns a string, to actually kind of create an actual L value out of it, and then deal with that. And again, Probably a comment for the C++ series, but just wanted to throw it in here. Why not? So back to our actual code. Let's get back on track. We've got our source. We've got a pointer to the actual source character data. The next thing we're going to do is actually called GL shader source, which specifies the source of our shader. You can see the first thing we want is the shader, which is just basically.
We should pass the ID and the source code, right? Yeah, I can see it from the arguments. So let's try to take a guess. So we have GL shader source, right? We pass the ID, right? The shader ID. So we pass the ID, and then we pass this source code, right? Wait, that's the fucking count. Probably this is the type. I don't know. Probably this is the type. This is probably the type, right? So and then we pass the source. I don't know why this is. Oh, I mean SRC. And it still errors out for some reason. Like if we go here, this is a const, right? It's a const char. It's a const character, right? And this is also a const character. I really don't get it, honestly. Const GL character const. Wait, is this something like this? How does that work? So we changed it, right? I don't know. Okay, let's follow his video. I was trying to think with my own brain.
ID. The next thing we want is count. So how many source codes are we specifying? Just one. The next thing it wants is an actual.
Okay.
Now you'll know that there are kind of 2 pointers here. It actually wants a pointer. This is a double pointer. It basically just wants a pointer.
Oh, it's a double pointer. Yeah, I noticed that now. So it wants this probably. Yeah, it's kind of tricky because there were two pointers, like 2 keywords and 2 pointers, and yeah, it was kind of tricky, but I get it.
To the actual pointer, so we actually have to give it the memory address of that source variable, and then the length. Now this is important. If you don't really want it to use the whole string or anything, you can specify it here. We're just going to pass in null pointer. Again, I encourage you guys to actually go to docs.gl and check out all of these kind of functions and make sure that you actually understand kind of the code that you're writing. I am mentioning a lot about how these kind of functions work in this series, just out of experience, but remember, knowing, for example, that you can pass null into length. Like if length is null, each string is assumed to be null terminators.
Okay, if it is null terminator, you pass null. Okay.
Stuff like that really does help to read the docs, and if I was actually trying to learn OpenGL properly, like I assume most of you guys are, keep this open as you go along with these videos and as you type this code, certainly, so that you know kind of what's going on. OpenGL tends to be very flaky in the sense that if you actually get a little minor detail wrong, you might just see a black screen and it might not work at all. Very, very soon we're going to have an episode about OpenGL errors and how to deal with them and my strategy for dealing with them, so that's coming up soon. We don't really, I haven't done it yet because we're just drawing something as trivial as a triangle, and really that you wouldn't expect that to go wrong, would you? I mean, it will, and it can and probably will for a lot of you go wrong. But very soon when we start to get into more kind of fun stuff, I am going to make an episode about OpenGL errors. But that being said, keep the documentation open, read it. With an API as fragile as OpenGL that gives you so little help when things go wrong, you want to basically master the documentation if you want to actually be good at OpenGL. Okay, so going back here, we've specified the shader source code. The next thing we need to do is...
So we have everything we have here. Yeah, we can also, yeah, I kind of understand this function, right? So we can also check it from here, like, right? So let's search for GL, probably shader source, and we have it here. So the shader specify the handle of the shader, so the ID, the identification number, right? Then we have the count to specify the number of elements in the string and length arrays. Alright, I get it. So we can pass, this is, we passed this is a double pointer, because we can have multiple strings to be compiled, right? Multiple sources. That's interesting. And if we have null pointer, that means it's null terminated, right? So the count specify the numbers of elements in the string and length arrays. And string specify an array of pointers. It's an array of pointers to strings containing the source code to load it into the shader. So we can actually create an array of strings, and then we can pass multiple strings and increase the count value here, and we can pass it multiple shaders, multiple sources in a single function call. Okay, that's pretty much how it works. And the length is null terminated, so we pass null pointer. That's interesting. It can also give us an error. So this is interesting. So what we have here, we have GI compile shader, right? We have shader source. Then we also have to compile the shader. So it's a different function call. So let's go here. Let's call GL compile shader, and we probably need to compile this ID, right? That's probably what is going to do. That's probably what is going to happen on that video that we are following. So I don't. This is the thing to get the attributes, right? Okay. So we probably have to pass the ID that we. Alright, yeah, it's right here. Then we have if. Okay, we can also check if this is compiled. And vertex compiled. If this is not true, apparently, log length, and then you can log the error, right? Yes, it write the error to a log, so we can also check if this is compiled correctly or not. It's like this is a handle procedure, so we can. So we have a similar process for the fragment shader, and it will get compiled like this and logged like this, right? And then we call this function GL create program to create this program from this two, and probably this should be called right here, and then we should return the ID of the program, which is return program, and this should return, of course, the ID, right? I'm just taking guesses, but I think this is pretty much how it works. Now let's try to jump back in the video and see if we did things correctly. The only thing we need to do is to handle the errors. So if we if we do this, so we have, okay, we have a pointer, we have to pass the reference IV. I don't know what is this IV. Wait, what is IV? So I know that's GL gas shader IV. I don't understand what IV stands for. GL gas shader returns in parameters of the output. The following parameters are defined. So we have the shader type, delete status, compile status, this part here. I don't know. Probably it's the type, it's the return type, probably. So let's also try to check if we did everything correctly. So if we let's just copy and paste this. So let's create an int. So if this is compiled, equals to, it's not assigned. So and then we call this function gl gl get shader iv equals to wait, it's not equal, it's a function this. So we have to pass the ID of the shader, and then we have to get the compile status. So compile status, and then we have to pass this as a reference, right? Because this will be assigned here. And then we check if compiled is equals to gl.ok or gl true. Okay. And if it isn't, we can also do this, like we have compilation error and things like this, things like that, std handle, or we can, you know, generate this log message. I don't know what is going to do exactly, but there is a log system here. Probably this is part of the, you know, this is a GPU thing. But yeah, we also have a log system here. But for now I'm just gonna print that out, and I will use a normal cout. Yeah, because I don't know. So I'm just taking guesses, right? Let's try to jump back on the video. And what the fuck is this? I don't know. I fucking hate Windows sometimes. And let's see if we did everything correctly.
Basically just say gl compile shader, and we need to specify which shader we want to compile, which in this case is just the shader ID. And
yep.
That is actually all the code that we need to write to compile that actual shader, so we can return the ID and everything is good. Now we're not doing any kind of error handling, so we definitely need to basically just syntax errors and stuff like this.
Oh, that's what we did exactly. Like this is the error handling system, right? That's basically what we did, right? This, I don't think this is probably. I will leave it as a to-do handle errors, because I probably this isn't completed. Like we just have the single compilation error. Probably there are multiple types of error that we should handle, but for me, like, for now, I think this is good, and this should be unsigned, I think. So
We need
let's.
to do some kind of error handling for this actual shader to see maybe we just accidentally, you know, missed a semicolon or something like that in our shader source code. We can handle all that in a minute. Okay, so going back to our create shader, we're going to duplicate this line of code, call it fs for our fragment shader, type in gl fragment shader, and
Yeah, that's what we did.
Shader source code over here. Once we've done that, we basically need to attach both of these shaders to our program. So think of this almost like compiling C++.
Okay. So this isn't the actual program that where it gets created, because actually we didn't pass anything, even though this is a stateful machine. So I don't know if there is any state here. Like we didn't write some binding, like we didn't call any binding function. So we probably have to pass this arguments as a, pass this two as an argument, right? Let's see.
Code. We've got two different files, and now we want to basically link them into kind of one program so that we can, well, use both of them. So we're going to type in GL attach shader. We're going to specify the program that we want to attach to, and then the actual shader. So we're going to do this two times, one for each shader, vertex shader and fragment shader. Then we're going to link our program by calling GL link program, which we just take in the name of the program, or rather not the name but the ID. And finally, we're going to type in GL val.
Okay, we were pretty close. Yeah, we just have to attach it, and then we have to link them. GL link program, probably. Yes, we have to pass the program. So this is literally the compilation process. So we compile each individual shader, then we link it together and we create a program, right? This is probably what I'm going to do.
Validate program.
We also have GL validate program. I don't know what that does, but let's hear it.
And these functions, again, are something that you should read about in the documentation if you actually want to understand what they do. You can kind of see that basically what this does is, well, performs validation on the actual program, and the kind of status of the validation, again, will be stored as part of the program's object.
We also have errors here.
State, which you can actually call kind of GL get program and query what, well, performs validation on the actual program. And the kind of status of the validation, again, will be stored as part of the program's object state, which you can actually call kind of GL get program and query what the actual result is and all that stuff. Again, I encourage you guys to read the documentation. I'm not going to explain these too much right now because it's kind of code you write once and forget about, so I don't really think it's important to talk about them too much. But definitely consult the documentation, especially if you have problems with your shader or you just want to understand more and be the ultimate OpenGL master. Finally, we can...
Of course, we want to be ultimate OpenGL master, so let's read the documentation right fucking now. So let's see. Wait, let's go here and let's search for it. And where is the syntax? I think sometimes IntelliSense doesn't work properly, but we have this. So GL link program, it just links the compiled shaders, right? We have GL link program links the program object specified by program. If any shader object type vertex shader are attached to program, they will be used to create an executable that will be run on the programmable vertex processor. In this case, I think it's the GPU, right? If any shader objects of type GL geometry shader are attached to program, they will be used to create an executable that will be run on the programmer. Okay. These are probably parts of the GPU, right? We have geometry processor, vertex processor. These are parts of the GPU. If any shader objects of type GL fragment shader are attached to program, they will be used to create an executable that will run on the programmer fragment processor. So let's try to check if we have where is the vertex processor? Like we have this processor vertex processing, the set of stages of the vertex processor is responsible for running the vertex shaders. The inputs for a vertex shader is the vertex data, namely its position, color, normals, etc. Depending on what OpenGL application sends, the following OpenGL code will send to the vertex processor a color and a vertex position for each method. Is this so? This is a stage, right? It's not a physical processor. So this is a stage. Vertex shaders, rasterizer, fragment shader, and the pixels will be returned. In Swift and Metal. Metal is the Apple API, right? Mac OS and probably iOS. Yeah. It's probably like this. Let's say I'm streaming. Yes, I am. So now let's. Oh yeah, we also need to, as a result of successful link operation. Okay, so hold on. The status of the link operation will be stored as part of the program object state. So it's always a stateful architecture. So this value will be set to GL true if the programming object was linked without errors and is ready for use. GL false, otherwise it can be queried by calling GL get program. Okay, with arguments program and GL link status. So we have GL get program. The same thing like GL get shaders. We pass the attributes. This attribute, it's a similar thing that we did here. GL get shader IV, and then we pass the ID, and I guess we have to pass the ID of the program. Then we have to pass the pointer, the address of this variable where we store the result, and then we pass the attribute. This is the attribute flag, right? This is pretty much how it works. So we can handle the errors. We always need to do handle errors, right? This is our to do thing. We get the GL program IV, and I'm not sure what IV means. Probably the GL, the return type, the variable type it is assigned to the output. Probably, I'm not sure. We have this is pretty much how it works. We have different types of error, but we can simply check if this is true or false and probably print that error, right? There is probably the log system here. I will probably do that later. So for now, I want to print the errors. I'll just print if there is an error or not. So a similar thing should be done here. So let's create a neat linked value. Then we call them GL program with get program IV. Yep, it exists. We should pass the program ID. Then we should pass the flag, probably GL link status, right? And then we pass the link as a pointer, right? This is pretty much how it works. And then we check if linked is not true, like this. And then we have std cout and then link error, just like this, right? This is probably how it works, right? Let's see. So should be an example at the bottom, and we have fragment compiled. Wait, where is it? Wait, this is the GL program, right? Where is it linked? It's usually at the bottom, right? If this is okay, program linked, we have IV program linked status, program linked. If this isn't true, it will log the error. This is pretty much what we did here, right? Yeah, so it's basically, this is how it works, right? So we should get the error and print that out. So I'm starting to, I'm slowly starting to know how this works. But yeah, there is a lot of things to learn, and so we have GL link program, and we also have GL validate program, right? And we also have the same thing for the pipeline, and it's only supported for the latest versions for the embedded systems and the GL4 and GL and the actual GL API, right? So we have GL validate program. GL validate program checks to see whether the executable contained in program can execute given the current OpenGL state. The information generated by the validation process will be stored in program's information log. Okay, so we have an internal log system that logs the errors or anything like that. The validation information may consist of an empty string, or it may be a string containing information about how the current program object interacts with the rest of current OpenGL state. This provides a way for OpenGL implementers to convey more information about why the current program is inefficient, suboptimal, failing to execute, and so on. So it gives some useful information, right, about your program. The status of the validation operation will be stored as a part of the program object state. This value will be set to GL true if the validation succeeded and GL false otherwise. It can be queried by calling GL get program with arguments program and GL validate status if validation was successful. So yeah, we have to, we probably have to validate the program here, right? Yeah, we already did this. So yeah, it's like it generates the messages and it will return some spaghetti code, or I don't know, like it returns some useful information, right? This is pretty much how it works.
Now that's because they've been linked into a program. So we can kind of delete the intermediates, if you will. In C++, when we compile something, we get intermediate.obj files, object files, when we're dealing with Microsoft's compiler. And at the end, we can kind of delete that because we've actually got an actual program now. They're stored inside the program. So we're actually going to call GL delete shader with VS and FS.
Okay, we can delete this because the program is already compiled and ready to execute. So let's delete the shaders. Delete shader. Wait, no. Wait. Oh, hold on. GL delete shader. Then we have VS and FS, right? Because everything is already compiled on this at this point, so we don't need them anymore. They will just take space, right? So let's delete the shaders, and yeah.
There are some other functions like GL detach shader and stuff like that, which will actually delete the source code. The reason I don't like to touch those functions, there's a few reasons. First of all, they're not really that necessary to even clean that up because it's takes a trivial amount of memory anyway. But
Wait. This reason aside, you should technically be calling GL detach shader after it has been linked. We'll talk more about this in a later video.
having the shader source code still around is very important when you kind of deal with things like graphics debugging, because if you kind of delete the shader from the GPU, the shader source code from the GPU, you can't verify and you can't kind of breakpoint and step through your shader like you can with certain NVIDIA tools, which we will get into. If you kind of detach your shaders and delete all the source code and stuff like that, you're going to lose a lot of that debugging ability. And to be honest, like a lot of game engines don't even bother calling GL detach shader because it's such a minimal gain that it's not worth it. And that's really all we have to do. We can finally return our program. Now you might have noticed that we're actually returning an int, whereas this program is an unsigned int, so I'm just going to clean this up so that it actually returns an unsigned int, and that is our shader. Let's quickly do this error handling, because I have a feeling when I actually write the shader in a minute here, it's just going to be wrong, and I'm just going to make a mistake, and then I'm going to be like, great, nothing works, and I'm going to have to end up writing this error handling code anyway. So let's just write it now. Much like we just wrote a OpenGL validate program setting like some kind of state and then we can retrieve it, we can also retrieve the result of this compilation. Compile shader doesn't actually return anything, however, we can query it to find out if anything's wrong. And the way we do that is by calling gl get shader IV. Now this is our first kind of introduction to I and V and all this, because get shader is really the function. IV is basically the types that it needs. So first of all, we type in the ID. Then we type in the parameter name in the form of an actual GL enum, which we know is an unsigned integer. Basically, this is just going to be a constant here that's defined by OpenGL. In this case, we're getting the compile status. And then an int parameter, which we know is just an int pointer. So I'm going to type in int result, and then pass in the memory address of that result. I basically specifies that we are specifying an integer.
That's what we did.
Specifies that it wants a vector, so an array kind of. In this case, it really just means it wants a pointer. Then we check to see if the result is equal to false. So if result equals GL false, now you might note that GL false, if I just hit Alt F12 here, GL false is just defined to 0. So you can also kind of specify if result with an exclamation mark to say if result is false. I usually do stuff like that. I don't like doing it here though, because we're specifically checking with GL false and not just kind of false or anything like that. This kind of just makes a little bit more sense, I think, to people watching as well, so I'll keep it as that. So if the result was false, means our shader did not compile successfully. What we actually want to do now is get the error message. And the way we can do that is basically
we should query the error. We should probably call it GL get error message. Do we have this? GL get error. We have function, and then we have GL get error. We have multiple methods here. Let's try to check the documentation just to get used to it. GL gets error. Probably you should use this. GL get error returns the value of the error flag. Oh, this is a flag. This isn't a string, this is a flag. So this is like a flag of the error. But we need a string, right? Let's check the let's keep going with
query the error message length first, So if I type in int length and then gl get shader ID, gl info log length, you can see why I just love OpenGL's API, because really it's just great. And then we'll specify the memory address of length so that it can store that data there. Once we have that, we can actually construct just a stack allocated kind of char array here. So message, I'll say, with the parameter length. Now.
Okay. No. Get the fuck out of here.
We get a little bit of a problem here that I don't like either. But you can see I can't just create a stack allocated length here because length
Has to
is
be a
actually a
fixed
variable
value.
and not a constant, and for some reason C++ just cannot grow the stack by an arbitrary size in some cases. We're not gonna, we're good though. We're above this kind of level of comedy, so we're actually going to hack this. I still want this to be defined on the stack. I could use something, most people will probably solve this just by making this a heap allocation and then kind of deleting it later, or maybe assigning it to
Yeah,
a
I would do
or something
that.
like that. I am not most people. I don't like this. I still want this to just be a normal char allocated on the stack. So what I'm going to do is actually set this equal to alloc a, and then the size being just length times size of char. Char being, of course, a lowercase char like that. Okay, and we're going to cast this result back to a char pointer, and we're going to get a pointer to that like that.
So yeah, we are gonna use the alloco. So that's this. So we have the length. Is this a assigned int? I don't know. Let's just follow the video. So we have the length. Then we have gl get program iv. Then we have the program. Then gl error. Wait. Let's try. Let's get the gl get program iv. Why is this blue? Like cyan? I don't know. So we have this flags. It's gl info log length. So we have to get the length and store it inside this variable. Of course, we make some stupid typos here, and then we can start to allocate the character, I mean the string, probably error string or something like this. And then we have a local. Okay, we can. This is a little bit weird. I will also specify size of characters. Yeah, I know it's just 1 byte, but some compilers actually have multiple. I have different bytes based on the compiled on the compiler and the platform. So I'm gonna use size of characters, and this will malloca. Okay. There is another method that is. This is. I don't know. Yeah, there is another method right here. I will use alloca. Okay, I will follow that video. Okay.
Allocate is a function that C actually gives you, which lets you allocate on the stack dynamically, like what we've done right now. Okay. Use at your kind of discretion. A lot of people don't like using stuff like this. There's no reason for not using it. It's a nice function. I like using it. In this case, it's totally necessary. And let's continue. I might actually make a C++ episode about this specifically because it's not as well known as it probably should be. Okay, the next thing we'll do is gl get shader info log.
Okay. So gl get shader info. Jesus fucking Christ. Get shader info log. Oh god. We have the shader. Wait, this is for each shader. So we have fs, like in this example. Oh my god. So let's try to, to check the documentation first. Gl get shader log, get shader info log right here. So this is the shader, the max length, the actual length. I'm just gonna follow this video.
Shader being ID, the buffer size being length, then it wants an actual length in the form of a pointer for some reason. This is going to be the output length, I guess, maybe. Again, should read the documentation. And then finally it wants a pointer to that actual buffer. So we'll just type in message like that.
Okay. So we have the ID of the program. I thought I was... Oh, that's the shader. Oh god, the shader is a program, right? I got confused with compile shader, and yeah, it's a shader that links the other two shaders, and it's, oh god, it's a little bit confusing, but okay, let's do this. So we have the length and the length, and then we have the error message. I will call it MSG, right? For some reason the ID errors. Wait, it's not. Wait, we need to do this. Wait, hold on. This part is actually, this part is right here. So we need the ID, right? Yeah. Okay, this was a little bit, I got a little bit confused. And then we have the other type of error here, and this is the link error, right? Let's keep
Then we're
going.
going to actually print the message to the console. I'm just going to use standard cout in this case. So cout message and end line.
Simple like that. So we have std cout msg and then std handle like that.
Before we actually do that, I might print a kind of fail to compile shader. Now we don't know which kind of shader it failed to compile at this point. So what we actually could do if we were really cool is basically just check to see what type the shader was. In this case, we know we're only compiling either a vertex or a fragment shader. So what I could do is, if I just kind of separate this code out like this, what I could do is write type equals gl vertex shader. If that's true, I'm going to actually move this down here so you can see what I'm typing. If that's true, we're going to write vertex. If it's false, we're going to write fragment. Again, this is a little bit hacky because we could have more than just these two shader types, but I think that's probably totally fine. I'm going to kind of bring this line back to being on one line, but I'll actually...
Okay, let's do this. So yeah, we can shader this, and I will probably do this. So if the type is GL vertex shader, that's vertex, or else it's a fragment, right? It's not that flexible because, as he said before, like we also have other types of shaders. So for now, let's just do this like he did here.
But anyway. Alright, cool. So we're printing a message saying that we failed to compile our type of shader, and then we're printing the message. Finally, we should kind of handle this result by writing GL delete shader, because of course our shader compilation didn't work out. And then we can return something like 0, because we are returning an unsigned answer, we can't really return -1. Okay, cool. There we go. Now we're not checking here to see if it works.
Wait. So let's GL delete shader, then we delete this ID, and return -1, I guess.
It didn't work out. And then we can return something like 0, because we are returning an unsigned answer, we can't really return -1. Okay.
Oh, okay, yeah.
There we go.
That's
now
right.
we're not checking here to see if it works or anything like that. We should probably assert or something like that if this doesn't work out, because it's kind of vital to our program running successfully. But anyway, we'll at least get the error message printing to the console. That should be enough to debug it in our situation here. Alright, cool. So that's all that we need. Now we can actually write a shader quickly and hopefully use it. So let's talk about writing some shaders now. We're going to come down here to just after we create all these buffers. It doesn't really matter where we do this. I might just do this after the kind of vertex attribute pointer. So first of all, we know that we can just type in unsigned int shader equals create shader, and then we just need to specify 2 strings, which are the source code, and that's it. So let's kind of just write our first shader, std string vertex shader equals, and now we're going to write our source code. Now this is
Okay, let's do this. Hold on, my ears hurt because of this. Hold on. Okay. So we have this part here, and now we have to get the shader, right? Probably here. So we have the shader equals the unsigned int shader, and then create shader for this, and then we have to pass the code, the source code for the shader, right? And yeah, that's what it did. We create a new string, and this is where the vertex shader or vertex source, I don't know, shader is compiled. So wait, how does this work? Oh my god, this is, I'm sorry, my ear hurts. So now let's keep watching this. So we probably have two strings right here, and one of them is like, one is the fragment shader, right? Fragment shader. So we have the vertex shader, then we have the fragment shader, right? Here we should have the code.
This is a little bit annoying to write as a C++ string because we have to put like a new line character after every line and all that. Super annoying, but we'll kind of do it anyway. So I'll kind of bring this down here to make it a little bit easier. First thing we're going to write is version 330 core, which basically just means that we're going to be using GLSL, which is OpenGL, which is the GL shading language, OpenGL shading language, version 330. And core means that it's not going to let us use any kind of deprecated functions or anything like that. That would result in a shader compilation, because we just want to make sure that we're using the latest and the greatest that we have. Now, the reason I'm not writing like 450 or 440 here is because we don't really need all those new features just yet. When we do, we will switch to using those more modern languages. And in this case, we're just ensuring a bit of extra compatibility. Now, I want to write new line character, and then I'm going to just press enter in C++. You don't need to write like plus or anything like that. If you just write strings kind of like this, one after the other, they will be concatenated into a single string. Okay, next we'll have just a kind of a blank line, just because. Again, I'll make sure I kind of write new line here. We don't really need to write new line. This is more for me than actual C++, but we'll actually do it anyway. And then finally, void main. This is our main function for our shader. I'm just going to open it up like it was any other function. You can see I'm already kind of forgetting to write new lines everywhere, which is fun. Another reason why defining these kind of shaders and files is a lot better, and we will probably...
Okay, hold on, let me just write all of this. This is a bit confusing, honestly, but let's do it anyway. Can we just use row strings?
We do that next episode. This main function works much the same way as our actual main function does in C++ when we actually have int main here. We're basically just specifying what function, this main function will get called when this vertex shader gets called. And what we basically want to do in here is just set GL position equal to our attribute, which is our vertex position, which we kind of specify over here, and we take in via a vertex attribute pointer at index 0. So how do we access this data? How do we access these two floats in our actual shader? Well, we need to specify the actual attribute up here. So I'm going to kind of add some space here and then specify the attribute. And I'm going to do this by basically typing in vec4 position. And then at the beginning of the line, I'm just going to specify that this actual attribute is located at index 0. And the way I'm doing that is just by writing layout location equals 0 like that. And then in vec4 position. So this 0 should be matching up with this 0. It is the index of our attribute. So one thing you might have noticed is that I'm taking in a vec4, however, I'm actually giving it a vec2. Why am I doing that? Well, first of all...
Oh my god, this is layout location 0 in vec4 position. This is... there is too much information for me.
This needs to be a vec4 eventually anyway, because GL position is actually a vec4, and we can't just assign a vec2 to a vec4. We could change this to be a vec2, but then we'd actually have to kind of convert it into a vec4 by taking in position.xy and then kind of specifying whatever we want for the other values, which would probably be something like 0 and 1. We don't really want to do that. Instead, what we can do is actually get OpenGL to convert this into a vec4 anyway. Remember, it knows this is a vec2. It knows this is a two-component vector because we've written 2 here. That's why it knows to cast this. And because it's an actual position, it's going to set the 4th kind of component, position.w, to actually be 1, which is what it should be if our vector is an actual positional vector. We might talk a little bit more about mathematics and OpenGL and how vectors work and all that in a future video, but just know that this is what we're writing for now. Okay, cool. That looks pretty good. That's actually all we need to do in our vertex shader. So let's just end that with a semicolon and let's write a fragment shader. I'm going to copy all this code here. Come down here, call this fragment shader. I don't need any of this kind of layout stuff, but what I do need to do, remember, is our fragment shader should be outputting a color. So I can keep layout location equals 0 here if I like. It's not really necessary, it will be 0 by default anyway, but I'm just changing this to be out, vec4, and then I'll just call this color. This version 330 stays the same. main function stays the same, but here we actually specify what color we would like to output. Let's try red. So I'm going to write color equals vec4 1.0, 0.0, 0.0, and then the alpha value, which is, we'll set that to 1. Okay.
So, okay, there is, hold on. There is so much information here to remember. So this is the GLSL language, okay? The OpenGL shading language. Wow, it's not that easy to remember things on the first time at least. But let's try this. I think I did everything correctly here, so everything should work.
Cool. So colors in graphics programming are traditionally just floats between 0 and 1 in kind of a non-HDR environment. So basically 0 is black and 1 is white. So if you're used to colors being between 0 and 255, think of 0 as 0 and 255 as 1.
Yeah, they're
so
normalized.
0.5, that will kind of be 50% red. And the way that these go is R, G, B, and A. Now this kind of RGBA layout and all that kind of depends on your actual frame buffers format, but for this kind of default setup, it definitely is just RGBA. So we should see our triangle as red now. That is all of the source code that we need to write. Hopefully I haven't made any errors. I don't think I have. Just checking to make sure I have new lines everywhere. I don't over here. That's not a big deal, but I'll add it anyway. And that looks pretty good to me. Cool. So over here under create shader, let's specify our vertex shader and our fragment shader, and hopefully everything goes well. We can bind our shader by just writing gl use program and then shader, and that's it.
Okay, we still have to, oh my god. So gl use program, and then we have shader. Okay, let's see if that
Our
works.
actual red shader should now be used to render this. I'm gonna hit F5 and hopefully we will see a red triangle. And we see a white triangle. And no errors as well. Fantastic.
Let's try to run this. Let's see if we have anything. Oh god, it crashed! Holy shit, we have an assembly error. What the hell? Okay, this isn't supposed to be like that. I don't know. Okay, this isn't supposed to be like this. Where do we? This is the Aloka. This is Aloka. Start checking on time. We subtract the register EX from the page size. Yep. Then we test. We test. Is this an actual instruction? I'm not really experienced with assembly. We should probably do this together. We should probably learn assembly deeply. But I think the error was generated from the alloca function, right? Let me check if that's true. I don't know. So we have this. I will allocate this dynamically. So let me just use malloc instead. I don't know. I feel like the error comes from here. So let's try to. Now we have an error here. Wait, is this null? Wait, what? Wait, why is this null? Why is this a null pointer? Wait, this is a null pointer. Wait, what? Also, it doesn't compile, it throws an error. Oh, wait. We are getting this weird errors. Let's try to check what we did wrong. GL info log length. We passed the right thing. We have the ID. If the result is false, so everything should be here, right? It should be correct, right? But for some reason it isn't.
Standard cout in this case. So cout message and end line.
For some reason it doesn't get compiled. Like this is the length. What is this value? This is a null pointer. This is null. It failed to compile, but it also fails to display the message. For some reason the length is this value. What the fuck? Seriously, what the fuck? Why does this return this type of value? Get. Oh, that's why. Oh my god, I'm dumb. This is a shader, it's not a program. Okay, that was. Let's do this here. And now, oh, it works, but there is an error, like an unexpected syntax error. Unexpected this, expecting this or this, a token this. This is a vertex error, so let's go back here. But it's red. it works anyway for me. I don't know. So we have okay, we also forgot this part, but yeah, this is the vertex shader error. So let's try to compile this again. And now we get no error, and the triangle is red for me. I don't know.
Before we actually do that, I might print a kind of fail to compile shader. Now we don't know which kind of shader it failed to compile at this point. So what we actually could do if we were really cool is basically just check to see what type the shader was. In this case, we know we're only compiling either a vertex or a fragment shader. So what I could do is, if I just kind of separate this code out like this, what I could do is write.
Oh, all right. This is the previous part.
You know, today we're living in.
Shut up.
RGBA. So we should see our triangle as red now. That is all of the source code that we need to write. Hopefully I haven't made any errors. I don't think I have. Just checking to make sure I have new lines everywhere. I don't over here. That's not a big deal, but I'll add it anyway. And that looks pretty good to me. Cool. So over here under create shader, let's specify our vertex shader and our fragment shader, and hopefully everything goes well. We can bind our shader by just writing gl use program and then shader. And that's it. Our actual red shader should now be used to render this. I'm going to hit F5 and hopefully we will see a red triangle. And we see a white triangle. And no errors as well. Fantastic. Let's take a look at what I did wrong. Okay, so just scroll.
For me, it's red.
Scrolling up here. And let's take a... Oh, well, there you go. GL vertex shader. Nice. I bet you guys had a...
Wait. Oh, right. That was the error. I wrote this by myself, if I remember correctly. I didn't follow step by step, but yeah, that was the...
Good laugh when you saw me write that. Make sure this is obviously compiling the type so that we're not compiling two vertex shaders. I'm actually supporting...
Yeah, that was the...
And we see a white triangle. And no errors as well. Fantastic. Let's take a look at what I did wrong. Okay, so just scrolling up here. And let's take a, oh, well, there you go. GL vertex shader, nice. I bet you guys had a good laugh when you saw me write that. Make sure this is obviously compiling the type so that we're not compiling two vertex shaders. I'm actually surprised that it worked. Well, actually, no, I guess this is a valid vertex shader because we are outputting color as just kind of a vec4. Yeah, that's all good. That would have been a valid vertex shader. That's why we didn't get any errors. We should definitely verify if our error messaging is working correctly. Let's just hit F5 and see if this works though. Alright, fantastic. You can see that we've got a red triangle and our shaders seem to work successfully. Awesome. Let's quickly just close this. I'm going to make a deliberate syntax error in one of my shaders, maybe in the fragment shader, just going to miss this semicolon here. Let's hit F5. Okay, so we don't get anything on the screen, and you can see in our log it actually does say fail to compile fragment shader, and it specifies that on line 9 we have an error because, well, it's
it works for me.
Syntax error. Fantastic. Thank you, Intel. It's great compiling that. Alright, cool. Anyway, let's go kind of back, let's revert back to our code. This is a very, very simple shader. We've just got a red triangle running. I'll just hit F5 again so we can see that awesome triangle. Pretty cool stuff. One more thing I want to quickly mention is that what you should do to clean up your shader once you're done with it, so maybe like over here, is actually called GL delete shader, and then the shader you want to delete. Now,
this should actually be delete program. Okay, so this should be, okay, let's just GL delete program, and then we will call the actual shader, right? So a shader is a program, but a program is a set of shaders, for what I understand.
we should also be doing this for kind of vertex buffers and all of that. We are going to abstract a lot of this stuff into classes. In fact, next time I'm going to show you how to actually read shaders in from files and my strategy for reading them in and how I like to kind of write shaders, because I don't like the way that OpenGL kind of makes you write them and all that. So we'll talk about that next episode. But as we begin to abstract this into files, we are going to cover actually cleaning up and all of that stuff, because that's going to get super important when we actually have a running program in which we kind of create and destroy things all the time, and we don't want to be leaking GPU memory or anything like that. Now, we're not going to go too far with the abstraction, of course, because this isn't a game engine series, but we are still going to abstract it a little bit so that we don't just write our entire program in one file. It's going to get very difficult when we have a lot of code to actually achieve certain graphics like effects and strategies and all that. So that should be a lot of fun. Anyway, I hope you guys enjoyed this video. If you did, you can hit the like button. If you want all the source code for this video, because we did write quite a lot, you can go to patreon.com/thechano, help support the series, and you will get access to a private GitHub repository with all of the source code, episode by episode, so you can just follow along to the episode you're currently on and all of that by just looking at the commit history. It's great. And again, you'll also be helping support the series, which is very important. There are also some other pretty cool rewards. For example, the top tier patrons, actually we have like a 1-hour hangout once a month where we just talk about pretty much anything. It's pretty cool stuff. Anyway, definitely check out patreon.com/thechano. Really does help support the series, so thank you so much to everyone who's helping make this happen. As always, you can talk about this episode by just leaving...
Oh yeah, that's basically it. So for today, what we did is, like, we enabled the vertex attribute buffer, then we specified what we specified what this data is. Like, the type is, the index is 0 because this is the position. Then we have two floats, and this is a float, and this is already normalized, so no need to normalize this. And this is the size in megabytes, and this is the pointer, so because this is the beginning of the array, right? Then we have the vertex shader, we have the fragment shader, and when we create the shader, we will actually create a new program, and on the program we will attach these two shaders that will be compiled here. And yeah, we will create this, we will pass this source, and then we will compile it, and we will check if there is any errors, and if there isn't any, we will return the ID of the compiled shader, and it will be stored inside these two variables. And then we attach this using the program ID and then the shader ID. then we will link it and validate. Then we will delete the shaders because it's already compiled. Then we will return the ID of the program. Then we will use this program, right? And then we can start drawing our triangle. And after this, we will and after we exit the loop, we will delete the program. That's what we did today. And for now, I will end the stream, and I will probably keep going with this or come back with the form application. But that is interesting. Thank you so much for joining the stream. Thank you so much for watching, and I will see you on the next time. See ya.